resync style snapshot copy negotiation. The primary Q tree is resynced to the specified snapshot copy on the secondary. The resync rolls back the primary Q tree to the specified snapshot copy, and an incremental restore transfer is initiated from the specified snapshot copy. Note that if no common snapshot copy is found, the incremental restore fails and an in-place baseline restore is attempted. Here's an example of an incremental restore. You're going to have to use the -r option in the SnapVault restore command to do an incremental restore. So at the primary storage controller, you type SnapVault restore -r. Then the $S, specify the secondary, the /vol / the name of the volume / the SnapVault Q tree you're restoring from. Then specify the restoring to with the /vol / volume name / primary Q tree. It will give you the confirmation warning saying this restore will override existing data in the /vol / volume name primary Q tree. Are you sure you want to continue? You say yes, it will start the process. We'll see that a resync will begin. The use of a common snapshot for that resynchronization will be utilized. And then you'll see that the SnapVault resync starts. Then it'll tell you that it was successful. It will tell you you can monitor the progress with the SnapVault status command, or you can abort it with a Control-C command. Tell you the time it took. It will tell you that the Q tree, the primary Q tree, is now writable, and it's completely successful. Both the in-place and the incremental restores are going to be non-disruptive restores. SCSI connectivity to the LUNs is going to be maintained throughout the in-place or incremental restores. The primary Q tree is made read-only. The LUN attributes in the primary Q tree are reserved in a temporary staging area. Then LUN maps are updated, and the external SCSI requests are processed using the information stored in that staging area. The hosts see the same LUN with the same drive letter at all times. Then, when the restore has completed, the LUN's attributes that are stored in the staging area are applied to the restored LUNs. The primary Q tree is broken to be write-enabled, and the I/O operations are resumed to the restored LUNs. In order to display the LUNs in this preserved staging Q tree area, you'll use the new data on tap command, LUN show staging. The example we see here starts with the original LUN's location being /vol / the name of the volume, san_vol1 / the Q tree, in this case Q tree 1 / the LUN, LUN1. Then for the staging Q tree naming conventions, the location will be /vol / the name of the volume / the staging _ then the volume UUID, a long series of numbers there, then _ a transaction ID. So in our example, we're looking at the LUN show staging command for vol / san_vol1 / staging _ long series of names to represent the volume UUID _ the transaction ID, long series of numbers there too, / LUN1. Happens to be a 100 meg online map LUN. Now, to resume the SnapVault incremental updates will resume only after the original backup relationship is restarted with the SnapVault start -r command. Note that the SnapVault copy created on the primary for the restore is not deleted automatically. Do not delete this snapshot copy as it's needed to perform this restart. Now, the SnapVault baseline in place and incremental restore operations present the following limitations. First, the I/O operations are not allowed during baseline in place and incremental restores. They support only Q-tree level restores. They do not provide restores at the LUN level granularity. And neither OSSV nor SnapVault volume to Q-tree relationships can benefit from these enhancements. Now, when integrated with Data ONTAP SnapDrive for Windows with the Volume Shadow Copy Service, or a VSS, this creates two snapshot copies upon LUN backup. A backup snapshot copy containing the LUN to be cloned, and then a backup snapshot copy containing both the LUN and the clone. Current versions of Data ONTAP, during the initial baseline transfer, SnapVault backs up LUN clones as new LUNs. The LUN clone and its backing LUN is transferred to the secondary system. Therefore, the LUN clone and its backing LUN get replicated as two separate LUNs on the secondary. This unoptimized transfer does not preserve space savings with the parent LUN. So now, in Data ONTAP 7.3, we have optimized the LUN clone transfer. In Data ONTAP 7.3, SnapVault is able to back up LUN clones in an optimized mode using SnapDrive. The LUN clones are transferred as clones, and space savings with the parent LUN is preserved. Note that LUN clone optimized transfer is available only with SnapDrive for Windows. In this process, the SnapVault initial baseline transfer is still performed at the command line, and the primary Q-tree must not contain LUN clones. Once the SnapVault relationship is handed off to SnapDrive for Windows, transfers must not be run from the command line. On the secondary, the backing snapshot copy is locked after the backup snapshot copy is transferred. So here are some of the limitations. In optimized mode, the primary Q-tree must not contain LUN clones. The transfer fails if the backing snapshot copy is missing on the secondary, and a SnapVault restore will also fail if the backing snapshot copy is missing on the primary. And finally, in optimized mode, cascades from volume SnapMirror destinations are not supported. So in summary, in this module, what we learned was how to deploy SnapVault primary and secondaries on the same storage controller, how the new Q-tree architecture improves SnapVault performance, and we saw how SnapVault in place and incremental restores can work in Data ONTAP 7.3. We also saw how SnapVault backs up LUN clones in an optimized mode to preserve the space savings of the parent LUN.